Hello viewers, I am Kausalya. Today we are going to discuss about derivation part of RLC transients. So here, this is the given circuit diagram. We are having R, L and C connected in series with the voltage source. And there is a switch which is closed at the instant when t is equal to 0. And I is the current that flows through this circuit. Right. Now the first step is we are going to apply KVL. So KVL is nothing but sum of voltage drop is equal to sum of voltage rise. So here in this case the source voltages are always considered as voltage rise. So here first we are listing out the voltage drops. So the voltage drop across the resistor is given by I into R and voltage drop across inductor is given by L into di by dt. And similarly, the voltage across the capacitor is given by 1 by C integral of minus infinity to t I into dt, right, which is equal to the source voltage E. So, the next step is just we are splitting this integral part into two, right. So, minus infinity to t is splitted into minus infinity to 0 and here it is from 0 to t, right. This is our second step. The next thing is here the limits minus infinity to 0 describes the initial voltage in the capacitor, that is before closing the switch. Is there any voltage across the capacitor? Right. That voltage is known as initial voltage. So here in this discussion, we are considering the initial voltage across the capacitor as 0. Therefore, this term will reduce to 0. Right. So when you make that term 0, here comes our expression. Right, I into R plus L into di by dt plus 1 by C integral of 0 to t I into dt is equal to E. Right. Now the next step is we are going to take Laplace transformation. So when you take Laplace transformation, you see I into R becomes I of S into R and here di by dt becomes S into I of S minus I of 0 plus and this capacitor term becomes 1 by Cs into I of S which is equal to E by S, right. So here I of 0 plus this denotes the initial current in the inductor. So in this case again we are making the value of initial current as 0, right. So this expression is reduced to 0. Therefore our expression resembles like this, okay. This is our expression, right. So here in this case, I am taking I of S commonly outside. So when you take I of S outside, here there is R and here there is L into S and here there is 1 by Cs, right. So now I am shifting this part to the right hand side. So this is our expression for I of S, right. Now the next thing is I am going to multiply this S with the terms inside this bracket. So when you multiply, what happens? Our expression becomes like this, right? S into R plus L S square plus here when you multiply by S, the numerator and the denominator S will get cancelled and here we will be having 1 by C, right? Now the next thing is again, I am going to take this L outside because we always need an expression in terms of S square, S and some constants. So here there is an extra L present here. So I am going to take that outside. So when you take that L outside, you see our expression is S square plus R by Ls plus 1 by Lc. Right. This is the expression for I of S. Now the next step is we are going to calculate the roots of the denominator because here we are having a quadratic equation. Right. So the basic formula to solve this quadratic equation is this is given by minus b plus or minus root of b square minus 4ac divided by 2a. Right. So here the value of a is 1 because coefficient of s square is 1 here. The value of b is r by l and the value of c is 1 by lc. Right. So just substitute these values in this formula and once you solve, you see here we are finally ending up with an expression like this, right. So here the thing to be noted is this 2 is common for all the numerator terms, right? So I am going to shift this 2 to the numerator part. So what happens? Minus r by l divided by 2 becomes minus r by 2l, right? The next thing to be keenly noted is now I am going to move this 2 to the square root part, okay? I am going to fix this 2 inside this square root. Therefore, you see, here the thing is, just when you solve and see, everything will be tallied, you see. Here there is r by l whole square, right, divided by 2. So the same thing, r by 2l the whole square. So 1 by 2 square is nothing but 1 by 4, right? So when you take square root, that becomes 1 by 2. So here is the 2. Am I making the things clear? Just I am shifting this 2 to the numerator part. Since as I am moving this 2 inside the square root, okay, here I am squaring this 2. Right, that's the thing. So the next thing is, you see, here I am moving this 2 inside the square root. So it is 1 by 2 square, right? So this 4 and 4 cancel each other, and finally I am ending up with an equation like this. Right. So here, since we are having a big derivation, that is big part of expression, I am simply writing it as alpha plus or minus beta. Right. So here the value of alpha is minus r by 2l, and the value of beta is, this entire expression is represented as beta. Right. So the next thing is, what is the purpose? Why we are doing all these things? Because we need to find the value of I of t. Right. That is the current that flows through your circuit. So here I of s is represented as, you see, again when you look back at the original expression, you see this is your expression for I of s. Okay, this is your basic expression. Now we have solved this quadratic equation and we have obtained result. Now, so we are going to replace this expression with the result what we have got. So here you see the value of I of s is again E by L. So instead of s square plus r by ls plus 1 by lc, here we are having this part, right? S minus alpha plus beta into S minus alpha minus beta. Because here the root is alpha plus beta and the other root is alpha minus beta, right? That's it. So next thing is, we are having 3 different cases. So we are going to solve one by one. So here the first case is, just we are looking at this part, right? So when this value is greater than 1 by LC, what happens, right? So when this value is greater than this, what happens? The value of beta will be positive, right? So therefore the roots are real and distinct. Okay, you will be having real values but different values. So again, when you write expression for I of s, it is written as k1 by s minus alpha plus beta plus k2 by s minus alpha minus beta. Right, just like writing in terms of partial fraction, that's it. Here we are having 2 terms, right? So here we are having 2 constants like this, k1 and k2. Again, when you apply inverse Laplace and solve this expression, right? So here is our final answer. That is k1 into e to the power alpha plus beta into t plus k2 into e to the power alpha minus beta into t, right? The next thing is, I am going to multiply this t inside this bracket. So here we will be having e power alpha t plus e power beta t. So the plus can be rewritten in terms of multiplication. Therefore, e power alpha t into e power beta t. Similarly, e power alpha t into e power minus beta t here, right? So in these 2 terms, you see e power alpha t can be taken commonly outside. So when you take this outside, our expression gets reduced like this, right? So here, when you have expression like this, okay, this is your expression for current. Then that current is said to be overdamped, right? So the current is said to be overdamped here. This is our case 1. So when you look at our second case, here you see when the value of r by 2l whole square is equal to 1 by LC. So what happens when the values are equal? Then the value of beta becomes 0, right? Because beta is nothing but root of r by 2l the whole square minus 1 by LC, right? This is our expression. When both the values are same, what happens? The value of beta becomes 0. So this is what written here, that is, you see discriminant is 0. So in this case, the roots are real and equal, that is, the values are same. So how to represent in terms of partial fraction? You see here the value of I of s is written as k1 by s minus alpha whole square plus k2 by s minus alpha, because here the roots are real and equal. Again, once you solve this expression, the value of I is given as k1 into, right, t into e to the power alpha t, and here k2 into e to the power alpha t. Right. Again here e to the power alpha t term is common. So just take it outside. So here the thing is k1t plus k2. Right. So the current in this case is said to be critically damped. Right. Now the next thing is case 3, that is R by 2L whole square is less than 1 by LC. Right. So in this case what happens? The value of beta becomes negative. So therefore the roots are said to be complex conjugate. Right. So when the value, that is when this is less than this, so beta is written as, so this is your bigger value now. Right. So square root of 1 by LC minus R by 2L whole square. Right. So here in this case the value of discriminant, or else you can just consider the basic expression here. You see this is your basic expression, right? So when this value is less than this value, what happens? The beta will become negative. That is square root of negative is, it gives rise to complex terms inside, right? So here we are having complex conjugate. Therefore here the roots are given as alpha plus j beta and alpha minus j beta. So while writing expression for current, this is our expression, right? So again when you write in terms of I of t, it is given by k1 into e to the power alpha plus j beta into t, and here plus k2 into e to the power alpha minus j beta into t, right? Again we are going to multiply and we are going to write this as two individual expression. So e to the power alpha t and e to the power j beta t. Similarly e to the power alpha t, e to the power minus j beta t. Right. So here in this case we are going to take e to the power alpha t outside. So when you take e to the power alpha t outside, this is our final expression. Right. Here the thing is, you see the constants k1 and k2 are said to be complex conjugate of one another. Right, what do you mean by complex conjugate? Just for example, you see, if one is 2 plus 3j, then the other will be 2 minus 3j. Right, if you have values like this, then they are said to be complex conjugate of one another. Right, so this is what represented here. You see k2 is nothing but k1 star. This means that we are having values like this. Right. So once you solve here, finally the value of current I can be written as e to the power alpha t a cos beta t plus b sin beta t. Right. So in this case, the current is said to be oscillatory, right? And at the same time, the current decreases. Okay. It starts decreasing. Now we will look at the graphs for all the three cases. So this is the respective graph, right? So here the first one is the current is said to be overdamped, right? So this is the respective graph, and in the second case the current is said to be critically damped, and in the third case the current is said to be oscillatory, right? You see here it is oscillating, and finally, and even what to say, and at the same time it starts decaying, right? Here you see the amplitude is higher, but in this case the amplitude is also reduced. So the third category is said to be the current is oscillatory, and at the same time it starts decaying with the time, right? So these are the respective graphs for your respective diagrams for your current in all the three cases, right? Here comes the end of this video. If you have any doubt, let me know in the comment section. Thank you.